Example 3, let's graph the function f of x equals log base 1/2 of x. The first thing we want to do is replace f of x with y, so y equals log base 1/2 of x. Now, it's easier to rewrite this in exponential form. The base is 1/2 and the exponent is y. So we have 1/2 to the y is equal to x. Now we can create a table and plot some points to graph this function. If you look at the expression, it's easier to plug in values for y because we will get values of x just by calculating 1/2 to a certain power. So we'll plug in -2, -1, 0, 1, and 2. 1/2 to the -2 is 4. 1/2 to the -1 is 2. 1/2 to the 0 is 1. 1/2 to the 1 is 1/2. And finally, 1/2 to the second power gives us 1/4. And we can easily check these values on a calculator. We'll plot 4, -2, 2, -1, 1, 0, 1/2, 1, and 1/4, 2. So as you can see, the graph does look like it decreases as it goes to the right. We'll draw in our vertical asymptote. Our vertical asymptote is on the y-axis. And here is our graph. It is decreasing forever as we go to the right. Our domain is from 0 to infinity. And our range is from -infinity to infinity. B, let's graph f of x equals log base 3 of x. So we're going to use the same idea. We'll replace f of x with y equals log base 3 of x. In this case, we have the base is a number larger than 1. The base is greater than 1, so we expect our function should increase rather than decrease. If a is between 0 and 1, then we know it's going to decrease. But in our case, we have a is greater than 1, so it should increase. We can rewrite this as 3 to the y equals x. And again, we're going to pick some points. We'll pick y values. So let's pick -2, -1, 0, 1, and 2. And 3 to the -2 is going to give us 1/9. 3 to the -1 is 1/3. 3 to the 0 is 1. 3 to the 1 is 3. And 3 squared is 9. Let's plot the points on the graph. We have 1/9, -2. 1/3, -1. 1, 0. 3, 1. And 9, 2. So it does look like an increasing function as we go to the right. And we do have a vertical asymptote as well on the y-axis. Example 4. We want to graph f of x equals log base 2 of x minus 1. I want you to note that there's a -1 here on the inside of the argument. So we know this is going to shift to the right 1 unit. And it's a base of 2. So we're going to have log base 2 of x be similar to our graph, except this -1 here shifts it to the right 1 unit. We'll start the process the same way. We'll replace f of x with y. Y equals log base 2 of x minus 1. Our base is 2. Our exponent is y. So we have 2 to the y equals x minus 1. Now it's time to plug in some values. And if you look, it's easier to plug in y and then solve for x. So I'm going to add the 1 to both sides first. And we have 2 to the y plus 1 equals x. Let's make a table and we'll plug in some values. Let's pick -2, -1, 0, 1, 2 for the y values, and then we'll see what we get for x. 2 raised to the -2 is going to be 1/4 plus 1, and we'll say that's 1.25. 2 to the -1 plus 1 is going to be 1.5. And we can easily check these on a calculator. 2 to the 0 plus 1 is going to give us 1 plus 1, or 2. 2 to the 1 plus 1 is going to give us 3. And 2 squared plus 1 gives us 5. So let's plot this on the graph. We have 1.25 comma negative 2. We have 1.5 comma negative 1. We have 2 comma 0. 3 comma 1. And 5 comma 2. If we need more points, we can definitely graph more points. But it looks like the vertical asymptote here is shifted to the right one, which makes sense because our graph is shifted to the right one. So let's draw a vertical asymptote. Here is our new vertical asymptote, and it is shifted to the right one. This is the equation x equals 1. Let's look at the domain. The domain is from 1 to infinity, and our range is from negative infinity to infinity. B, let's graph f of x equals log base 3 of x minus 1. Notice this negative 1 is on the outside of the argument, so I'm going to shift my graph down 1 unit because this is similar to log base b of x minus h plus k. So the h would move the graph left or right, the k would move it up or down. In this case, the k is going to move our graph down 1. So we're going to replace f of x with y. Y equals log base 3 of x minus 1. Now we have to be careful here because we cannot convert it to exponential notation unless we get the log by itself. So let's add 1 to both sides first. So I have y plus 1 equals log base 3 of x. Now we know that y plus 3 try that again. We can add the 1 to both sides, and we have y plus 1 equals log base 3 of x. Notice the log is by itself, and therefore y plus 1 has to be the exponent. So we have 3 raised to the y plus 1 equals x. And now we can make ourselves a table. And we'll pick some points for y, and then we'll evaluate the x. So let's pick negative 2, negative 1, 0, 1, and 2 again. 3 raised to the negative 2 plus 1 is going to be 1/3. 3 to the negative 1 plus 1 is 1. 3 to the 0 plus 1 is 3. 3 to the 1 plus 1 is 9. And 3 raised to the 2 plus 1 is 27. Make sure you check these numbers on a calculator to make sure they're the same as mine. We'll plot 1/3 comma negative 2. 1 comma negative 1. 3 comma 0. 9 comma 1. And in our case, 27 comma 2 doesn't fit on the graph, but it gives us a general idea that it should be increasing. And here's our graph, and we'll draw a vertical asymptote. We have the y-axis is our vertical asymptote again. Domain is from 0 to infinity, and our range is from negative infinity to infinity. Part C, let's graph f of x equals log base 4 of x plus 2. First thing we want to note is there's a 2 on the inside of the argument, and that's going to shift my graph to the left 2 units, so expect it to shift to the left 2 units. We're going to replace f of x with y, so y equals log base 4 of x plus 2. The base is 4 and the exponent is y. So we have 4 to the y equals x plus 2. And I could subtract the 2 to both sides and have 4y, or 4 to the y, minus 2 equals x. So let's pick some points, x comma y. And we're going to pick negative 1, 0, and 1. I don't really need to pick 2 and negative 2 because those will not fit on my graph. So we're just going to stick with these 3 points. 4 to the negative 1 minus 2 is going to be 1/4 minus 2, which is negative 1.75. 4 to the 0 is 1. 1 minus 2 is negative 1. 4 to the first power is 4. Minus 2 from it, you get 2. So let's graph the points on the graph. We have negative 1.75, comma, negative 1. We have negative 1, comma 0, and 2, comma 1. Since our base is 4, we know this function is going to increase. And according to the graph, it does look like an increasing function as we approach the right. And we also have a vertical asymptote. So our vertical asymptote is shifted to the left 2 units, as you can see here. Let's state our domain. Our domain is negative 2, comma, infinity, and our range is negative infinity to infinity. The properties of logarithms enable us to change the form of logarithmic statements so that products can be converted to sums, quotients can be converted to differences, and powers can be converted to products. Properties of logarithms. For x being greater than 0, y being greater than 0, a being greater than 0, and a not equal to 1, and any real number r, the following properties hold. The product rule says log base a of x times y equals log base a of x plus log base a of y. So the product rule states that we can change a product into the sum of two logarithms. The logarithm of the product of two numbers is equal to the sum of the logarithms of the numbers. The quotient rule. The quotient rule states log base a of x divided by y equals log base a of x minus log base a of y. This is saying the logarithms of the quotient of two numbers is equal to the differences between the logarithms of the numbers. So if I have a division of logs, I can just separate it into a subtraction. The power property states log base a of x to the r equals r times log base a of x, which simply states that if we have an argument with an exponent, just bring it to the front and you'll have r times log base a of x. But you could also go backwards. We could also bring the r to the exponent and we will get an equivalent statement. The logarithm of a number raised to a power is equal to the exponent multiplied by the logarithm of the number. We have the logarithm of 1, which states that log base a of 1 equals to 0 for any base a. All this is saying is a raised to the 0 is equal to 1. Remember, the answer to the log is always the exponent. A to the 0 is equal to 1 by definition, so log base a of 1 is always equal to 0. The next property states that if you have log base a of a, that's equal to 1. That's clearly true because a to the 1 is always equal to a. And remember, the exponent is always the answer to the log, so that's why this one is true as well. Example 5, let's rewrite each expression. Assume all variables represent positive real numbers with a not equal to 1 and b not equal to 1. Let's solve log base 6 of 7 times 9 and simplify it. So we have the product rule states that log base a of x y equals log base a of x plus log base a of y. So we're going to use that property for this problem. And that says log base 6 of 7 plus log base 6 of 9 is equivalent to the previous statement. We'll try to evaluate these if possible. 6 to what power gives us 7. Well, there's not a good number for that, so we'll leave this as simplified. 6 to what power gives us 9, and that's also not possible without a calculator, so we'll leave this as our solution. There are some situations where you have to answer log base 6 of, let's say, 36, and this is asking 6 to what power gives us 36. And in this case, I would say 2. So log base 6 of 36 can be replaced with the number 2. So that's why we have to check to make sure we couldn't simplify any further. B, let's simplify log base 9 of 15 over 7. And we're going to use the quotient rule, which states log base a of x divided by y equals log base a of x minus log base a of y. So we're going to, let's rewrite this with the quotient rule. We have log base 9 of 15 minus log base 9 of 7. And that cannot be simplified further because 9 to what power gives us 15 is not easy to answer, and 9 to what power gives us 7 is also not easy to answer. So this is a good solution. It cannot be simplified further. Part C, we want to simplify log base 5 of the square root of 8. So let's rewrite this so it looks like the power rule. I know that the square root of 8 can be written as an exponent. Let's say log base 5 of 8 to the 1/2 power. And using the power rule, we can bring this number to the front. So this is equivalent to 1/2 log base 5 of 8. And that's it. We can't simplify that any further. Part D, let's rewrite log base a of the cube root of m squared. And we'll use our formula from the past, which is the exponent rules. X to the m over n is equal to the nth root of x raised to the m. So I can rewrite this as a rational exponent again. So this is equivalent now to log base a of m raised to the 2/3 power. And now we can use the power rule to bring that 2/3 to the front. So we have 2/3 log base a of m, and this is our rewritten expression. Part E, let's rewrite log base a of mnq over p squared t to the 4th. I'm going to start with the quotient rule first, so let's break up this fraction. So this is equivalent to log base a of mnq minus log base a of p squared t to the 4th. Then we could use the product rule for the three terms here, m, n, and q. So this is log base a of m plus log base a of n plus log base a of q. So that's from the product rule here on the left. Now on the right, we have a negative symbol here, so I'm going to be extra careful, put the negative here, and then we'll simplify this using the product rule. So we have log base a of p squared plus log base a of t to the 4th. Now we can distribute the negative through the right side. We have log base a of m plus log base a of n plus log base a of q minus log base a of p squared minus log base a of t to the 4th. And now we can finally use the power rule. The power rule states we can bring the exponent to the front. Here's our final answer, log base a of m plus log base a of n plus log base a of q minus 2 log base a of p minus 4 log base a of t. And this is our final solution. Part F, let's rewrite log base b of the nth root of x cubed y to the 5th z to the m. So let's rewrite it as a rational exponent first. We have this is equivalent to log base b of x cubed y to the fifth over z to the m raised to the 1 over n. So I could use the power rule first. This becomes 1 over n times log base b of x cubed y to the fifth z to the m power. So now we have this is equal to 1 over n, and we can use the quotient rule. 1 over n times log base b of x cubed y to the fifth minus log base b of z to the m. And now I can use the power rule for x cubed and y to the fifth in addition to the product rule. And we could also use the power rule for the log base b of z to the m. So this is equal to now 1 over n times 3 log base b of x plus 5 log base b of y minus m log base b of z. So remember to use the product rule first to separate x cubed and y to the fifth with addition, and then bring the power down with the power rule. Example 6, write each expression as a single logarithm with coefficient 1. Assume all variables represent positive real numbers with a not equal to 1 and b not equal to 1. So we'll start by looking at the expression and figuring out when can we use product rule, power rule, and quotient rule. Notice that in the first expression here, we have an addition sign, so we can use the product rule. So I can rewrite this as log base 3 of x plus 2 times x minus log base 3 of 2. Since this is a subtraction symbol, we can use the quotient rule. So this simplifies to log base 3 of x plus 2 times x over 2. And now we can simplify the numerator, and this is equal to log base 3 of x squared plus 2x over 2. Part B, let's simplify the expression into a single logarithm. 2 log base a of m minus 3 log base a of n. Let's use the power rule first to bring the exponents to the top. And so we have this is equal to log base a of m squared minus log base a of n cubed. And now, since we have a negative in the middle, we can use the quotient rule. So this simplifies to log base a of m squared divided by n cubed. And that completes our problem. Part C, we have 1/2 log base b of m plus 3 over 2 log base b of 2n minus log base b m squared n. I always use the power rule first, so let's bring up all of these exponents to the top. And we'll be careful when we do that. So this is equivalent to log base b m to the 1/2 plus log base b 2n raised to the 3 over 2 minus log base b m squared n. Now let's use the product rule for the first expression. This is equivalent to log base b of m to the 1/2 and multiply that by 2n to the 3 over 2 minus log base b of m squared n. We can now use the quotient rule. Log base b of m to the 1/2, and I could distribute the 3 over 2 to the bases. So this is 2 raised to the 3 over 2, n raised to the 3 over 2. We're going to divide that by m squared n. And this is from using the quotient rule. This is equal to log base b of, and then we'll have to simplify the argument. We have m to the 1/2 over m squared, and so that simplifies to m to the 3 over 2 in the denominator, and I did that by subtracting 1/2 from 2. We have 2 raised to the 3 over 2 in the numerator, and we have n and n to the 3 over 2, and that simplifies as n to the 1/2 after we subtract the exponent here. And this is our solution to part C. A word of caution, there is no property of logarithms to rewrite a logarithm of a sum or difference. That is why in example 6a, log base 3 of x plus 2 was not written as log base 3 of x plus log base 3 of 2. The distributive property does not apply in a situation like this because log base 3 of x plus y is one term. Example 7, assume that log base 10 of 2 is approximately 0.3010. Find each logarithm without using a calculator. So I can rewrite this as log base 10 of 2 times 2, which is the same thing as 4. And this is equal to log base 10 of 2 plus log base 10 of 2. So all we have to do with this expression is add 0.3010 twice. So this is equal to 0.3010 plus 0.3010, and that gives us 0.6020, and that is without a calculator. We want to rewrite log base 10 of 5 without a calculator again. Our argument here is 5, our argument here is 2. So we have a disconnect between the arguments, but maybe we can rewrite 5 as something else. Let's rewrite log base 10 of 5 as 10 divided by 2, so we can introduce the 2 into our argument. And I know 10 divided by 2 is equivalent to 5, so this has the same value as log base 10 of 5. I could use the quotient rule now, so this is log base 10 of 10 minus log base 10 of 2. Now we know that log base 10 of 10 is equal to 1. The reason for that is 10 to what power gives us 10. Remember, the answer to the log is the exponent, so in this case this is equivalent to 1. And we know that 0.3010 is log base 10 of 2. So we can fill that in, and now we can subtract these values without a calculator. Subtracting these numbers, we get 0.6990, and the work is done without a calculator. Theorem on inverses. For a greater than 0, a not equal to 1, and the following properties hold. A raised to the exponent log base a of x is equal to x for x greater than 0, and log base a of a raised to the x is also equal to x. The following are examples of the applications of this theorem. We have 7 raised to the log base 7 of 10 equals 10. Log base 5 of 5 cubed is equal to just 3. And log base r of r raised to the k plus 1 is just k plus 1.